All right. Okay, so today we're wrapping up Maxwell's equations. We had two more things to do that both involve time varying electromagnetic fields. The first one is Faraday's law. Now Faraday's law is actually has a very unique. I don't think you can say very unique. Has a unique place in the development of modern physics because the reinterpretation of what magnetic induction looks like was actually the thing that brought Einstein to say that to realize something was wrong in our interpretation of motion, and he said that all motion must be relative, and the rest is history. So that's Faraday's law, and I'm not going to completely retrace those steps, but there are a couple of tricky points in looking at Faraday's law where you need to really follow exactly what it says, and even then, it's still easy to misinterpret. So I hope we'll be able to show you all the dangerous spots. And then, of course, the second one is the displacement current. So that's the time varying electric field. And of course, the displacement current was that thing that was missing from Maxwell's equations to be able to explain electromagnetic waves, right? So if you have an electromagnetic wave, which we will start on next week, you have a time varying magnetic field that causes a time varying electric field, and then the time varying electric field in turn causes a time varying magnetic field. So today we'll put both of those time varying dependencies in Maxwell's equations, and we'll have that. But the displacement current was missing. Now there are many ways in which to arrive to the displacement current. There is the and I'll show you two ways to do it. So there's the way that you've probably seen before, where you have a charging capacitor and then you mess around with Amperian surfaces, and they show there must be something that looks like a current that actually is represented by a time varying electric field. That's an intuitive argument. It works really well. So we'll run through that argument as well. There's another one that is just using a vector identity, but that has a tendency to become a little bit circular because there's a vector identity for the magnetic field that it needs to satisfy, and the only way to do that is to actually include the displacement current. The only problem is that you start with the continuity equation, and of course the continuity equation comes from Maxwell's equations once you include the displacement current. So unfortunately, there's no way to untangle this, and you have to decide for yourself which argument you find more appealing. I find it more appealing to say that charge must be conserved, and that's what the continuity equation says. We talked about this a couple of weeks ago, right? So you have a divergence of J is minus ddt of rho, and then if you make that into volume integral, it's very clear to see that if the charge inside of that volume changes, it must be because there's a current that's flowing out of it or into it. I think that's an entirely reasonable point of view, but it's only there in Maxwell's equations once you include the displacement current. I'll show you how those two are related, but yeah, at some point you have to decide where to start. Now, of course, it's not a mystery that it's there. It's not. I mean, there have been millions of experiments done. In fact, we're doing an experiment right now that shows that there must be a thing called the displacement current. So just the fact that pedagogically sometimes we have a hard time finding the right path into it doesn't necessarily mean that it's not one of those things that it's people don't look at it as much as Michelson-Morley interference experiments, which people still look at and try to prove Einstein wrong. Anyway, different discussion. So we'll do that, and then we do have to talk about where the energy is stored when we have a magnetic field, and surprise, it's in the magnetic field. Now, also there are many ways into the material. So the book actually shows you two, and one due to Feynman, which of course can do no wrong, and then another a little bit more mathematical, which is also fine, but I'm going to take a different approach, and I'll show you that it must necessarily sit in the magnetic field because that's how Faraday's law works. That's how Lenz's law works. And that's how inductors work. So I actually use an inductor to show you where the field is stored. So slightly different approach, but I think it's actually a little bit more tractable because you can really see what changes when you change something. And then so that should wrap up this chapter. So we'll be able to burn through this chapter in one day, which means the next chapter is going to be whatever the next number is. I'm really losing track. 6, I think. So electromagnetic waves. Okay, so let's talk about Faraday's law. Okay, so Faraday's law just says that if you have some time-varying magnetic flux, that there's an induced EMF, and that induced EMF is like a voltage source that can then afterwards drive currents through secondary circuits, which is the basic mechanisms of electric energy generators, of electric motors, of inductors. There's a whole realm of devices that are built on this principle, and of course, at its heart is the curl of E, which is so the curl of E. Of course, we saw that when we were looking at Maxwell. I call it Maxwell 2, which is basically the circuital law for an EM. We said that if you have a closed path through an electric field and the field is static, then if you come back to the starting position, then no work will have been done. Or phrase it in another way, the potential, which is the line integral of E through some kind of an electric field, is a function only of the position, not how you got there. Both of those are saying the same thing. Both of those are saying that the field is conservative. So usually, we would put 0 here, and of course, if you want to be pedantic, you put a 0 vector. Now, of course, that only works if we're doing electrostatic. Now we're not doing electrostatics anymore, so we have to take this out. So we're putting in minus dB dt. Okay, so that's the time varying magnetic field, and of course this is Faraday's law, and this is the way I number them is my Maxwell 2, and this is it's a little bit easier to see what's happening. What's happening here is if you change this into integral form. So if we're taking the integral of EDL, then that is the same as over some closed path. Then that is the same as the curl of E dotted with a surface, and then integrating over that. And now the curl of E, of course, according to Faraday's law, is minus dB dt. So we get a minus dB dt dotted with ds. And as usual, this is the edge of contour, which is the edge of that surface S, and that's the surface S. And these are related. Oops, these are of course related. And if B is uniform, so if B is uniform, over S, oops, come on, over S, then it's the world's most simple integral. Then we just have a ddt of B integrated over S, and then we can take the integral out, and we just get E is minus ddt of the integral of B ds, which is of course the flux. And this is the magnetic flux as opposed to the electric flux. This is saying the same thing. So let's see what happens. So we have some kind of a coil, so a loop, and we have a magnetic field here. And if this field is a function of time and presumably also position, then all of the field that threads this loop integrated over that surface area, if that changes, then that means that there's an EMF induced in this loop, and that's the EMF is of course this scripted E, so that's the EMF. Oops. EMF, or the electromotive force. And that electromotive force has the same units as the potential, because it is based on a line integral through the E field right there. So because it has the same role as potential, it just looks like a battery. So if it's like a battery, that means that it will have units of volt or stat volt in the Gaussian system, which means that it can drive a current. So as a result, we're going to get a current. So then the current gets induced and it starts to flow here. And then that's the induced current due to E. Okay, now there are limits to how big that current can be, and we will try to put numbers on that first. But first, we need to talk about what does it mean when the flux changes. So, what does it mean when phi b changes? So if you look at Faraday's law in differential form here stated quite clearly that there's really only one way in which you can generate an infinitesimal dE that you can integrate. Let me actually write this. This is dE, such that when you integrate it, it becomes E. So there's only one way to do this, and that is by having a time-varying magnetic field. Okay, well, how do you get a time-varying magnetic field? Well, that's actually that's a little bit ambiguous, because, for instance, what we could do is we could take a loop, and we could take a little bar magnet. So a bar magnet, and then there's the North Pole, South Pole, and then that means there's a magnetic field lines. Oop, oop. Okay, so the magnet has some magnetic field, and we can, for instance, we can move the magnet towards the loop. In that sense, the field here that is observed here and that is threading that loop is a function of time, because the field is stronger the closer you get to the magnet. And of course, if you pull the magnet through it, then the field reverses sign, but that's not the point. The point is that you can get a time-varying magnetic field this way. Now, another way to do this is to actually take the loop and do the reverse. So instead of having the magnet move, you would have, I'm running out of colors already, you could actually move the loop towards the magnetic field. Now, this is actually, this is a rather subtle, this is actually a rather subtle difference. So in the green case, it's very clear that the magnetic field here is time varying because you are actually changing the field that the loop sees. But there's a very different way of looking at the yellow situation. So you have a wire that's moving through a magnetic field. Now this wire, of course, carries charged carriers, because it's made of conducting material. So when you move a wire through a magnetic field, you're going to get a Lorentz force, and that Lorentz force is going to drive a current. So it turns out that Lorentz force is actually exactly the same thing. So it doesn't really matter whether you take the point of view of the Lorentz force is pushing the charges around or the flux is changing. Both of these will tell you that there's going to be an induced EMF, and therefore also therefore you're inducing a current if this loop is actually closed. Okay, so those are the two different points of view. Now, I believe this or a variation thereof was the thing that was the pivotal argument in Einstein's 1905 paper, but I'm not reviewing that argument here. So those are not the only ways in which you could change the time varying magnetic field. There's of course another one. So for instance, if you have the same loop here, but now instead of having a current source, instead of having a permanent magnet, we have some kind of a solenoid here. And of course, this solenoid, if we change this current, will generate a magnetic field. And the magnetic field, we know, is going to be proportional. It's going to be proportional to the current that is running through here. So that's the current. And if we vary the current, then therefore the magnetic field here varies. Therefore the flux that this loop sees varies, and therefore you get an induced EMF, and therefore you get a circulating current if you have a closed path. All right. Then there's another way in which you can get an induced EMF, and that is actually if you have a magnet, and instead of moving the loop closer to the magnet, you actually rotate the loop. So for instance, that's similar to the situation I had above here. So we have again our magnet, and then we got our field. Oops, let's make that red. And now, instead, what we do is we rotate this. And when this thing rotates, the flux that this loop sees, the magnetic flux that this loop sees, changes because, oh, come on. Well, I'm not changing this to red. The flux here changes. So the flux changes, so therefore you, according to the flux rule, get an induced EMF, and therefore you get a current. But if you look at this formulation of Faraday's law only says something about a dB dt. But here we're not actually changing dB dt because we're doing this in a region that we could even assume that the field is uniform. The fact that this field varies as a function of position doesn't really matter. It's the field that is threading that loop that is inducing an EMF. And again, here you can say, well, that's easily explained by using the Lorentz force. So Lorentz force on charged particles or charge carriers in the wire pushes the charges around, and you actually get the exact same EMF that you get if you were to ignore the fact that it's the loop that's changing its angle with respect to the to the magnetic field. And then finally, there is a there's another one where you say, well, if you have a let's say there's a magnetic field here, so B field. Okay, so this is B. And now this is this is made of conducting material, so this is a conductor. And now I place a rod here, and this rod is also conducting. And I'm going to move this thing around. So for instance, I'm moving it from here to there. Now, what I'm doing is I'm changing the flux that this loop sees by physically changing the loop size. And also this is easily explained with the point of view of the Lorentz force, where you say, well, there are charge carriers, you know, just say there's some kind of a Q here that's going to experience a Lorentz force and therefore is going to be moved through the circuit. So, so there are many ways in which you can induce this. There's a famous one which is still cause for a lot of confusion that I'm not going to get into, but if read Feynman, it's the source of the Faraday paradox. And it basically has to do with what happens if you have a conducting disk in a magnetic field and you spin it around. Do you see an EMF or do you not see an EMF? And people still argue about it, which is fun. So, but needless to say, a dB/dt is not the only way in which you can induce the EMF. And I think the cleanest way to say it is to say that E is minus d dt of phi b. And I'm using the total derivative, not the partial derivative, because we can change this flux by any way, right? We can do, oops, we can use the chain rule, and we can say it could be, you know, it's B dA. So we can change this as a function of time. We can change the dot product as a function of time, right? So if we rotate the loop around, or we could change the surface area as a function of time. And we can even move the entire loop. So basically change the contour integral as a function of time. Either one of those, as long as that thing seems to be changing, then we will get an EMF. And that's why oftentimes you'll see this thing with a total derivative rather than a partial, to make it explicit that you have to look at all these second order effects. Okay, so one way in which to see this is to say, well, the flux, it's, even if you have a uniform field, is B times A, where we say A is that normal. So you can write this as B times A times the cosine of the angle between the B field and the A field. And then if you want to get a time derivative, it could be B, it could be A, and it could be the alpha. That changes. The energy in the B field and inductors or inductance. Okay, so let's say we have some magnetic field. And we have a wire, and it's a loop, and we're moving it, let's say, out of the field with some velocity. And then this is a problem that I oftentimes ask students in my Physics 226 class on midterms and finals. Don't tell anybody. So it goes as follows. So all right, so 1, what is the EMF? 2, what is the current? 3, what's the work done? And what does that mean? So let me walk you through the argument. So first of all, the EMF is not that hard to calculate because there's a boundary here between the field and this part's in the field, and then as a function of this speed, usually we take uniform speed. As a function of this speed, we have an induced EMF due to the Faraday's law in flux formulation. And then if you have a, let's say we're doing this not too quickly. So for instance, we're putting a resistor here. Oh, make life easy. So we're putting a resistor here, and then it's easy to calculate the current. And this is actually sweeping something pretty big under the rug, but I'll get to that in a little bit. But let's assume that we don't have to worry about that. We can calculate what the current is, and then as this loop is moved through the barrier between the region with the field and without the field, that current is rotating, and that current is dumping energy into the resistor, and that means that there's going to be energy dumped in this resistor, and it's going to get hot. Where's the energy come from? Well, if you work out what the Lorentz force is, the Lorentz force is actually going to go exactly in the opposite direction. So the Lorentz force has to go in the opposite direction because that's the force that you're doing work against. And then we usually will complete this and we'll say, well, there's actually this thing that happens where because there's a current, there's an induced magnetic field. And there's an induced magnetic field, which means this induced magnetic field, according to the law of Lenz, which I will get to in a little bit, the induced magnetic field, the induced B, will attempt to compensate for the ddt of the flux, but that's the red flux. So you've probably seen this before. That's Lenz's law. Oops. So in other words, looking at this loop, loops moved out of the magnetic field, it's losing the red field lines that are pointing into this iPad, and therefore it's going to try to generate a field to compensate for that by generating a field that has the same magnetic field direction as the ones that it's losing, and therefore that's the induced direction of the field. Now, if the reason I bring this up, if you work out what the energy is that is being generated, it turns out that that energy is actually, that's dumped in that resistor, is exactly equal to the energy that you have done work against doing the work against the Lorentz force. Now, what if R is 0? Well, if R is 0, there's still going to be an induced magnetic field. And in fact, all of the energy that was before dumped in the resistor is now going to go in the creation of that green magnetic field. So it's perfectly legitimate to say that an E integrated over time tells you exactly how much energy was used to create that magnetic field B. And of course, this is, ignoring R. Okay, now there are there are real limits to how big that current can get, and that has to do with inductance, but that's not even the point. The point is that if this energy is work is being done, then that work goes into something else, and that something else, if there's no resistor, has to be the only other thing that's changing, which is the creation of the magnetic field. All right, so let's apply this way of thinking to the solenoid. So let's say I'm having some kind of a solenoid, and I'm driving a current through this solenoid, and then as a result, I'm getting a time varying magnetic field if that current varies as a function of time. And now I'm going to put my loop here, and then the way of thinking is, well, one, the current as a function of time, creates B. All right, and then two, the EMF is generated in here, so there's an EMF here. Three, a new field is generated as a result. So let's assume that it's increasing just to make life easy. So this is the induced field. Of course, these field lines are going to B is created, and in the same way as we were talking before, we're going to say, well, the work that goes into generating the induced field, the yellow field, we can find by taking the integral of that EMF over time. I'm not sure when my video paused, the recording paused. I'm assuming everybody is up to speed. But yeah, the idea is there's an induced EMF in the green loop, and it'll be there because the time varying current generates a time varying magnetic field, and that generates a time varying flux, and therefore we get an EMF, and therefore we get a B. Now, we're going to do that for the very idealized situation where we have an infinite solenoid model. So the blue solenoid is an infinite solenoid. So therefore, the field is uniform inside the solenoid. And we're going to calculate B. And then afterwards, we will calculate the EMF on that, on the green loop.
Dr. Postma?
right, shouldn't be too hard. So we started with, get rid of these. We started with just your straightforward Amperian loop. We integrate our magnetic field over some kind of an Amperian path, and the Amperian path is this red path here. This red path here. And then the B field inside the solenoid is non-zero, and the B field outside of the solenoid is 0. So the outcome of that integral is just B times whatever the length of that path is. The length of the path we're calling oops, squiggly L now, so lowercase l, because we will need the uppercase L in a little bit. So while the solenoid might be infinitely large, the Amperian loop is not. So within it, there will be n windings, and we end up with a magnetic field here that is proportional to the number of windings per unit length, so n over L, and of course proportional to the current. And then the EMF that's induced in the loop, that's this green EMF here, that's just your dDTB times A. We're not changing the surface area, so just get a dDT of B of A. At some point, we will stop carrying all the signs, because at some point it becomes a little bit tedious. But for completeness sake, we'll put this sign here. So yeah, so that's our induced EMF. It's just the dDT of the current. Actually, I did that wrong. Oops. It's the dDT of the current, of course. Now here comes the really interesting part. So we are right now treating the green solenoid or the green coil as distinct from the blue coil, but really there is no reason to think that any of these turns, let's say, let's call it this turn, that any of these turns actually experiences the same EMF as the green coil, because it is part of the solenoid. But honestly, this wire, it's a continuous wire, and it's made of atomic particles, and they don't have a collective consciousness of which particular circuit they belong to. So for any point in this circuit, we could be asking the question, what is the induced EMF that this solenoid feels? And then we would say, well, for every winding, like the yellow winding that I just highlighted, we need to count one EMF according to the green loop that we have just calculated the EMF for. So that means that the EMF induced by this loop in itself, which is self-inductance or self-induced EMF, is just N, basically the number of wires. So self-inductance, self-induced EMF is E in the blue solenoid due to its increasing field, B, and therefore flux, is just N. So that's E is N times the other E that we had. So that's our 4 pi N A over CL d dt of I. So in other words, the EMF that the blue solenoid induces in itself is equal to this expression. And if we want to know what the total energy is, we have to just say the energy that's stored is going to be the integral of I times E dt. So that means that we could take this E, plug it in here, we'll get a whole bunch of stuff in front, and we'll have an integral of I and an I prime, and then a dt, which is the same as an integral over just I, which is the same as 1/2 I squared, if I just goes from, let's say, 0 to I, some value. So this prefactor is the prefactor that depends only on geometry, and that's the prefactor that I'm going to circle here. And that prefactor goes in here, and we will call L for inductance. So L is the inductance. And this is the energy that's stored in the inductor. And if you work out what the energy density is, it turns out that U is also equal to 1/8 pi b squared integrated over the volume of the inductor. Okay, so moral of the story, for any kind of system, we can always go from a current creates a B field that creates an EMF, and that integrated over time gives you the energy stored in the inductor. And since B is proportional to I, E is also proportional to I, and therefore you will always end up with U being an integral of something, I dot from the EMF and the flux. Oh, sorry, that's going to be EMF. And then times I times dt, which is always going to be dot 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 1/2 I squared if you go from 0 to I. So this thing in front is always going to be something that depends only on the geometry, and we always call this inductance. Now there is a similar thing that we can use when we do when we consider them distinct parts. So there is this thing called mutual inductance, which is actually how we started, but actually it turns out to be a little bit harder to calculate because you can't physically, it's hard to calculate. But anyway, the mutual inductance is basically what the induced EMF in a secondary coil is as a function of the current that runs in the first coil. So it doesn't actually look like this, but for mutual, so for mutual inductance, mutual, not self-inductance, you get a U that is 1/2 times, big M, I1, I2. So that's the mutual inductance. So for instance, this one is driving a current, and then this one is being induced as a result. So that's what mutual inductance is. All right. So we've done the dB/dt. Now for the dE/dt, aka Ampere Maxwell. So the classic way of looking at how this comes about is with the following thought experiment. So let's say I have some kind of a wire, and there's a current that runs through this wire, and as a result, there's a magnetic field that is induced, and Ampere's law says that it has to go this way. Yes, I believe that's correct. And of course, these are not the only field lines. There's also lines that go bigger. That's not the point. So Ampere says that the B dl is mu naught I over C, and then this is a closed integral. And that's all fine. Now, what happens if instead of having this wire be a continuous wire and a really, really long wire, what happens if we interrupt it and we build a nice little capacitor here? So you should all be familiar with capacitors. So this is a capacitor. And now our magnetic field, there's no reason to assume that it would be different. We now need to be really careful with what we mean by this current. So the argument goes that actually the current is the current that pokes a hole in the Amperian surface under consideration. So for instance, it could be this Amperian surface. But actually Ampere's law does not really place any limits on what that surface needs to look like as long as it is bound by this contour. So we could, let's say this is a soap bubble and some kind of a soap membrane, and we blow in it, we could actually make this thing go like this. Now, this becomes a problem because now there is no current that is flowing through our Amperian surface, but there's definitely a magnetic field here, because why wouldn't there be? So there's something missing here. And of course, the answer is, well, this is a capacitor, this is not a wire. So why were you even assuming that things would be the same? So we have to think a little bit about what's happening when we have a current that goes into a capacitor. So when we have a current that flows in this direction, we always assume that that means that that is modeled by positive charges, right? So that means that this thing becomes positively charged. Now, these positive charges, they're accumulating on the left plate, and they have nowhere to go because charge is conserved, but more on that later. And now we have positive charges here, so therefore there will be negative charges being pulled from the right side of the wire into the right plate. Now, that motion will be left moving negative charges, aka a positive current going to the right. So the charge buildup, the charge buildup induces, and this is the electric induction, E, not B, induces opposite charge in the other plate. And therefore we get a current. All right. So in other words, the current that flows in the right part of the circuit is the result of the buildup of charge, not the charge, but the buildup of charge. So the current is the result of a Q of t that is taking the derivative off, right? So if Q is stationary, then there's no current, right? So, but only when it changes is there current. Now, because that charge is changing, the electric field in the capacitor is also changing. So I'm going to draw the electric field now. So the electric field points like this. And if you want to think about it this way, the electric field is actually that thing that is pulling those negative charges in, right? Because the electric field is the thing that mediates the Coulomb interaction. So these negative charges have no business being there unless they were told to be there by a Coulomb force, which is mediated by an electric field. So this electric field is the reason they're all there. But it's not the electric field that causes them to change. It's the changing electric field that induces a current. So therefore, this ddt of Q actually is due to a ddt of E. So the thinking goes, okay, we can fix Ampere's law to deal with situations like this by including another current. So let's fix Ampere by including a current that is proportional to dE dt. And that is the displacement current. Now, you can actually, you can work out what that expression is supposed to look like for the highly idealized situation where, for instance, this is a parallel plate capacitor, infinitely large plates, et cetera, et cetera, et cetera. There's nothing wrong with that, but I would prefer to do it in a slightly different manner. So we'll do this a little bit differently. And we will actually start with the continuity equation. Hang on a second. Where's my continuity equation? Okay, so we have talked about this before. Continuity equation, aka charge conservation. We have the divergence of J is equal to minus d rho dt. Now we're gonna need this, and we'll need that in a little bit. So let's see how this works. So let's say if we have the curl of B, we know that that is 4 pi over C times J. Now, we are allowed to take the dot product of this thing, and it should still hold. I should move these to the right. I don't know if I can do that. Let me just move it to the right. Okay, so minus d rho dt. And that should still hold. Now, this is actually a vector identity. So the divergence of a curl of any field is supposed to be 0. So this is 0. Now this is minus, and we can swap the divergence and the ddt the divergence of J. Now you see that according to this definition of doing this wrong. Sorry, this is not d rho dt. Hang on a second. Of course, this is supposed to be the right-hand side of ampere, which is what I had originally. 4 pi J over C . 4 pi J over C, all right? So that means this is minus 4 pi over C times the divergence of J, which is now, according to this vector identity, 0, which cannot be because otherwise the charge is not conserved. So how do we fix that? Well, we fix that by inserting a term that once taken, once added to ampere Maxwell is going to make sure that we have a d rho dt here. Okay, so how do we do that? Well, we have a divergence of J, and we need to add something that once we take the divergence looks like rho, and fortunately we have the divergence of E being 4 pi rho. So if we use that and add that with the right factors of 4 pi and C to this, we can actually make the right-hand side out here come out to be minus d rho dt. And the choice is therefore to reformulate Maxwell, Ampere's law, and make it look like this: 4 pi J plus 1 over C dE dt. Okay, so hopefully you can track what's happening. So now if you plug this thing in, you take the divergence of J, you also need to take the divergence of E. Now the divergence of E is going to give you rho through Gauss's law, and then you have a ddt of rho, and now everything is fine because now you have a divergence of J and you have a ddt of rho, and that is charge conservation, and everything is okay. So this is, of course, now called Ampere-Maxwell. And this term on the right is called the displacement current. Now, I would personally say it should be that times C over 4 pi, such that when you write this, you can write this as curl of B is 4 pi over C, and now we have a J plus a J displacement current, and that J displacement current is that thing that came from the right there. And of course, this thing is not supposed to be there. That happened when I was introducing our, when I was moving and inserting the Nabla operator, I was copying it down, and then all of a sudden there was a DDT that showed up here. Of course, it's not supposed to be there because this is the right-hand side of Ampere's law. So summarizing, we have our curl of E is minus ddt of B, with the caveat that sometimes we need the integral form minus d dt of phi b, and we need to assume that that phi b can be changing in many ways. And of course we have Gauss's law, that's 4 pi rho, and then we have Gauss's law for magnetism, which is 0 because there's no monopole. And then finally the one that we added, it's 4 pi over Cj plus 1 over C dE dt. And these, ladies and gentlemen, are Maxwell's equations. Okay, ladies and gentlemen, we've done it. We have completed all of Maxwell's equations, and now we are off to the races. So first order of business, Maxwell's equations, putting them to use, getting those two time derivatives to do some work for us, meaning electromagnetic waves.